Okay, just to try to finish these off. Actually, number 12 is very straightforward. It is just finding the max and min values. So sometimes you're going to find two values and determining the min is the second derivative set to 0. Unless it's hard, then don't bother. And graph each function is another thing. So first of all, this is simply a growth curve that's elevated by 2. So that means it's going to have a horizontal asymptote here at y is equal to 2. It's going to have a couple points here, which would normally be 0, 1, but it's going to be 0, 3. And then the other point, which would normally be 1, e, is going to be 1, 3 plus e. And, that's 5.71 or whatever. So you're going to see a curve like this. It goes through those points. Something like that. And since it's a growth curve, it's not going to have a max or min. You can figure this out when you take the derivative. The derivative is just that. And when does that equal to 0? It doesn't. You cannot have a 0 with an exponential. This, however, is a growth curve multiplied by x. So each value in the beginning, since x is negative here, it's going to be in the negative zone. So as soon as x is minus 1, plus 2, plus minus 1 over e to the x. So it's going to be a little while before it's negative, but there's going to be a period of this where this is negative, and then it will take off like a growth curve. And it'll be even accelerating up even more. But there will be a negative part in here. And I believe you might even see something like this. Let's see. No, it'll probably be hugging. Might be hugging here. Interesting. It's probably maybe something like that. Anyway, let's take the derivative and see. The derivative of this is the product rule. So you get ex plus x times ex, and that's because the derivative over here is 1, and the derivative of this over here is that. When you take ex out of it, you get 1 plus x, and then you set that to 0. So when x is minus 1, we will have a max point. Max point. And when you put minus 1 in here and minus 1 here, you get minus 1 over to the e to the 1 plus 3. So it'll still be positive. Well, let's try that again. Negative 1 divided by e equals plus 3. Yeah, it'll be positive. So I'm going to see a point here at negative 1, that. Now my big question is it possible to have big values of this and become negative? And I don't think so, because as this gets bigger, this exponent becomes really big. But right near 0, right near minus 1, what happens when x is 0? We get 1 here, and 0 here, and we get 3. So we have another point, 0, 3. This is going through the y-axis there. However, this would appear to be a min, so my guess is it's going to hug the y curve. Come through this point, come through this point, and then go shooting up. It's going to be a weird min. Now, to figure out if that's a min point, we can take the second derivative. Second derivative of this is this. Then it's the product rule again. Ironically, you're going to get a very similar thing. And when you set that to 0, take or sorry, when you put the minus 1 in there, you get 1 over e plus 1 over e minus 1 times 1 over e. So you get 1 over e plus 1 over e minus 1 over e. You get a positive number. If it's a positive number, it's a min. So because the second derivative turned out positive, this is indeed a min. I'm curious what it looks like. Yeah, okay. It can't ever get into negative numbers because of that plus 3. And because the growth curve never lets this part become bigger than 3. So it's hugging, comes down. There's our min point. There's our y-intercept, and off it goes into space. So pretty much as finally figured out. What about this one? Let's figure out the first derivative. First of all, let's associate the 2 with the 2x. So this derivative is this. Okay. And the second derivative is this. Okay, so you can take 2e to the tx out of both of them, and you get 2x plus 1. When you set it to 0, this can't be 0, so it's only this. When x is equal to minus a half, you will have probably the same thing. Also, let's figure out when x is 0 here. We get 1 and 0, 0. So it's going to go through 0 and 0 because there's no plus 3. We will have negative numbers wherever x is negative on the left side of the axis. So I'm suspecting we're going to have something like this, and then something that goes shooting off into space. When I put minus a half in here, I get 2 times minus a half. That becomes minus 1. And then e to 2 times the negative a half again becomes negative 1. So really you have 1 minus 1 over e to the 1. So minus 1 over e. When I take that, I get this. So at minus a half, I will find another min at this. I know it's a min just because of the nature of the curve, and yeah, I could go through the second derivative and figure it out. But why? This one's more interesting. Oh, and if you want, you can graph that, but I'm not going to bother. Just plug it into Desmos. This one's first derivative here, we got to take the product rule here. I get 3x with a minus times e to the minus x when I take the derivative of that. And I'm just doing the product rule here. And then I've got 3, which is the derivative this time, to the e minus x plus x, plus 1. So when you set that to 0, the question would be, I believe these cancel out. Let's just make sure of this first derivative. So the minus 1 goes in front. Get minus 3x. Oh, there's an x there. Okay. E to the minus 3x because that just stays there. I've put the 3 with the x, so the derivative of the second one is 3. Just times that. And the derivative of this is just plus 1. Interesting. So there's an x here, there's a 3, so these can't be added or subtracted because there's an x in this one and there's no x in that one. I can't take a 3e to the minus x out of it because I can't factor out that. Interesting. If I set it to 0, the question becomes, when is this whole thing equal to minus 1? At that point, I can take an e to the minus x out of it. I can even take a 3, and I can even take a minus. And I'm left with x plus 1. Now, you cannot figure it out because it's equal to minus 1. And it makes the determination of this very, very difficult. Let's go back to the original function. And take an x out of it. We're left with 3e to the minus x plus 1. This is now the product rule, might make it a little bit easier. So what's the derivative of that? Just 1. Plus x times the derivative of this, so this minus 1 comes down. You get minus 3. X and minus x minus 3 e to the minus x, and the derivative of that is again nothing. So you get the same problem. This has an x to it. This has nothing in front of it. You get obviously the same derivative with the same problem. I'd like to sketch that. I'd love actually to see how to solve that. I just don't want to take too much time on it. X minus x plus 1. Huh. Oh, plus x. Okay. Makes sense. It didn't look like the derivative is solvable. And actually, now that I think about it, even in this form here, for this to equal 0, well, no, that could have an impact. Okay, let's move that to the other side. Is equal to x, 3e to the negative x. So when can 3e to the negative x plus 1 equal to x times 3e to the negative x? See, the problem is, just because we can't solve it doesn't mean it can't exist. And the big factor here for me is this x multiplying it. Creates a potential factor where this could exist, because this is always going to be a positive number. This is always going to be a positive number, but this doesn't have to be. With the x, when the x is negative, it can become a negative number. Graphing it obviously makes it clear there is no max at all. And then the last one. What is the last one? It's a little bit... Oh, that's the one we just did. Okay. Kind of a waste of time. It doesn't really teach us anything other than how to get confused in some of the derivatives. So we have a profit. Try to remember profit is revenue minus cost. And it's very interesting and similar to the one we just did where x is bigger than 0, so they're only starting at 0. When x is 0, it's clear this whole thing's 0, so it goes through 0, 0. Find the max value of the function if x is measured in hundreds of units and p is measured in thousands of dollars. Okay, so we've obviously got to take the derivative of this. So we've got a interesting situation because of this. You'd actually never ever see this, but okay, so we've got to take the derivative of this first thing, which is 1, times this function here. Then we've got to add x times the derivative of this function, which is just this function, times the derivative up here. 2 times minus 5 becomes minus 1, and this becomes x. So multiplied by minus x. So we've got an x and an x. So it becomes minus x squared. And now I can factor out the common term. And I get 1 minus x squared. Set it to 0. Clearly this can never be 0, but this can. When is x squared equal to 1? Well, when x is 1 and when x is minus 1. Interesting if that's true. Fortunately, we can ignore this because we're only concerned with x bigger than 0, so this is only the valid answer. When x is 1, we get 1 times e to the negative 0.5, which is the same as 1 over e to the 0.5, which is the same as 1 over e to the half, which is the same as 1 over square root of e. So you get that. So in thousands of units, this would be this. It's going to go through that point at the max, which means you're making 100 units for a max profit of $606.53. Thousands of dollars, okay. $665, $6,065.30. But you're going to see this as the actual units. Here, not that. Unless I multiply everything by 1,000. Okay, let's see it. Hopefully I got it right. Again, I find a lot of these questions kind of useless. I think they're just trying to get you to stretch your derivative brain a bit. And zoom in, and yeah, so nice to know that our predictions were correct. And 0.60, so yeah, it's rounded up to 0.607. And there it is. And it was interesting to find this one to note there's probably going to be some symmetry in it. And I bet you, anything we find, I bet you P of 4 will yield me the opposite of P of minus 4. Yeah. So one has a negative, but the value itself is the same. Okay, pretty much answers that. Yeah, I mean, I guess it's better than the other ones. Okay, let's look at this curve. Let's read the question clearly first too as well. You're walking out of your home. You're looking at a graph that's distance based on time. So your home is probably your x-axis. When time is 0, this whole thing is 0. So you're starting at 0, 0. Let's get rid of the messiness. There we go. Graph this relation. So we have a straight line, and this 2 to the minus t is the same as 2 to the t down here. Normally this would be a growth curve, but when it's 1 over the growth curve, it's a decay curve. So we're getting a line that's probably going to be dominant, and then the decay curve is going to take over. So it's going to hit up, and then it's going to hug the 0 line. Right here is probably our point of interest. So we're going to come away from the house, and we're going to come back, and guess what? We're never, ever going to get back to the house, because that can never be resolved. That will always be a big number. And as a result, this will be insignificant, and as a result, the result will be close to 0, but never reach 0. Determine when the speed of the moving door is increasing and decreasing, so essentially find the max point. On this side, it's increasing, and this side, it's decreasing. Oh, it's the door closing. Closes quickly at first, then closes more slowly. In fact, the model of the movement. So, graph the relationship. So you can take a couple points. But I can tell you on the left side, the line will be more powerful and negative. And this is essentially a decay curve. Oh, and actually, yeah, the decay curve on the left will be more powerful, so the line's going to be way down. And then as the decay curve becomes smaller numbers, I believe believe it's going to go huge. Interesting. Let's just take some numbers, though. So there's definitely 0, 0. What happens at 1? And let's rewrite it. 200 times t over 2 to the t. So at 1, we get 200 divided by 2. And at 2, we get 400 divided by 4. Interesting. Which I think that'll stop it. So there's probably a max somewhere in there. And then at 3, we get 600 divided by 9. So that's where the thing's 200 divided by 3. So we get 66.66. And at 4, we get 800 divided by, sorry, that's not 9, it's 8. 600 divided by 8. So when we divide all things by 2, we get 300 divided by 4, 3/4. So that's going to be 150.75. And when it's 4, we're going to get 800 divided by 16, which is 100 over 8, which is, geez, 10, 11, 12, 12 point something. So it's definitely going to go up and then quickly come down, and then looks like it never closes. Determine the maximum speed of the moving door. That would be the inflection point right there. At what point would you consider the door closed? Never. Okay, so there's the graph. Determine the speed of the moving door is increasing and increasing, so there's going to be a peak somewhere here. So let's find the derivative. And we're going to write it the way it was. 200. We'll associate the 200 with the t just so we don't get confused. We'll keep it in this format for the derivative. Okay. And what's interesting about this is, have we done derivatives of growth? Yet have we proven that the growth curve derivative is that times the ln of 2 times the derivative of that yet? Are we just supposed to graph it? Okay. Anyway. I think I'm just going to graph it. Oh, I've got to switch everything to X. Probably going to quit after this one. I really don't find it that useful. And was it 200? 200t, 2 to the minus t. Okay, they've got it like this, but I don't really think we need it like that. Okay, so indeed the peak will happen right here, almost between 1 and 2. And it really peaks up from the 100. Let's look at P1. Let's just call it F. Let's look at F1. Yep, F2. Yep, so that's good. Should I try to take the derivative of it? Okay, the derivative of this one's 200 times that function plus the derivative of this function, which is the function times ln of 2 times -1. And then when I set that to 0, I see that I can take out 2 to the -t. You get 200 plus minus ln 2. 2, and there's no t in there. Oh, I forgot to multiply by 200t over here, because I've got to take the main function. So there's a 200t in this one. So I could take the 200 out as well, and I get 1 minus ln 2 of t, which means ln 2 times 1 is equal to that, which means t is equal to 1 over ln 2. 1 over ln 2 is, hopefully I got it right, no, I got it wrong. No, maybe not. Yeah, 1.44. I got it right. And then when I put it back into that function, what did I determine? 1.422. That's 1.442. Why is it giving me 103? Oh, 106. Oh, it doesn't go up that much at all. It's just this. There we go. Let's label this to 1 to 110. There. Okay. So we did get it using the derivative of the growth curve. Now the inflection would be the derivative of this, or if you want the derivative of this, which is a pain in the butt, because you've got to do just this derivative and then the product rule here, because there's a 200t in here. No thank you. Let's find the inflection point. Will be somewhere here, and it's when the f double prime of x is equal to 0. So there's the inflection point. So if I just do the curve of it, it's when 2.885. And that will be the fastest speed of the door. And that will be the max point. And notice the door never shuts. Yeah, it looks like 0 there, but zoom in. It can never really reach. See, no matter what, never going to reach it. When can you actually consider the door closed? Oh, 18 seconds, 20 seconds, 22. Depends what your definition of closed is. For me, it never closes. Not going to answer that. Yeah, so it's saying that population growths actually don't go exponential forever. They hit a limit. And of course, in society, nah, I'm not going to do all this. But if you look at nature, let's say you have rabbits and wolves and grass. Okay, and let's say the rabbits eat the grass and the wolves eat the rabbit, and the grass eat the decaying wolves. So if you have an increased explosion of rabbits, the grass is going to go down, and let's say the wolves are only attracted when there's a certain amount of rabbits, so suddenly the wolves come in, which means now that the wolves have come and the grass is gone, the rabbits decline, and then the wolves are happy until a certain amount here, and then the wolves go away. But now that there's no rabbits, the grass comes back, and the grass would grow as long as there's enough soil. But of course, now that the wolves have left, there's a couple of hidden rabbits that they didn't find, and now there's enough grass to eat, and the cycle repeats. The other limiting factor is if there are no wolves, once the rabbits run out of food, they will either die off or leave. So there's only so much square footage that can sustain a certain environment. And in nature, you get everything balancing off just as the way the wolves were, but there's going to be like in a square meter, you're going to see a trillion creatures at play balancing out the ecosystem. Now, obviously, a square meter of Earth isn't really an ecosystem. You'd look at a whole forest, and they have different terms, or you'd look at an entire climate, or you might look at a riverbed. It all depends on where the boundaries of various creatures. And that's the other interesting thing. Suppose the bear exists along this entire river, but the salmon only exists here, let's say, or that's not fair, not salmon, but some patch of insect that only travels along this route. Well, that ecosystem changed dramatically wherever those new life forms interact. I should read the question. It says, many populations grow exponentially, food available is sustained, population will level off, or like gold mines is a good example. Once the gold ran out, people left. So population will level out to a maximum attainable level called L. That becomes more important in university. Limiting value L. Oof. No thank you. I don't like the conceptual questions, but at university that will definitely take hold.